Hello, my name is Chris Horn. I'm a software engineer on the Lustre team at HPE, and this is a demo on how to troubleshoot LNet multi-rail networks. This demo is actually a follow-up to a talk that I gave at the Lustre Administrator and Developers Conference in the fall of 2021. So I'll start by providing a very brief recap of that talk from LAD. Next, I'll discuss the demo environment, and then we'll cover the demo topics, which involve showing how to view the state and activities of LNet Health, demonstrating how the multi-rail feature is affected by the peer discovery feature, showing how the primary NID is referenced by Lustre, and finally, how LNetctl Ping can and cannot be used to find broken paths. On this slide, I've provided links to the event page as well as links to the recording and slides for my talk from LAD. In that presentation, I discussed an overview of the multi-rail feature, including basic motivation and solution design, as well as the role of the primary NID as a convenient identifier for a multi-rail peer. I also discussed important statistics that can be used to validate that the multi-rail feature is behaving as expected. And finally, we took a closer look at the LNet Health feature. The LNet multi-rail feature allows multiple interfaces on the same LNet network, and it allows multiple LNet endpoints, or NIDs, to be associated with a single peer. This allows us to simplify the configuration that is needed to enable multiple network interfaces, and it lets LNet fully leverage available network capacity. Now historically, one LNet NID was equivalent to one LNet peer. But now with multi-rail, we have multiple LNet NIDs associated with a single LNet peer. So we need to give Lustre, or other users of LNet, an easy way to target messages at a peer rather than target a specific endpoint. This is where the concept of the primary NID comes into play. The primary NID is simply a way to uniquely identify a multi-rail peer. The first NID that is configured on a node is designated the primary NID. The primary NID is also used as a key for modifying peer definitions with the LNetctl command line interface. LNet maintains tallies of the number of messages that are sent or received to and from both local network interfaces as well as the interfaces of LNet peers. These statistics can be used to demonstrate that interfaces are being utilized in the expected manner. The LNet Health feature assigns a health value for each local network interface and peer network interface. Healthy interfaces are preferred over unhealthy ones when LNet is selecting the source and destination interface for a send. This brings us to the demo portion of the talk. We'll begin with a description of the demo environment. The demo environment consists of two virtual machines. On the top left, I have a terminal open to the server VM, and on the right, a terminal to the client VM. On the bottom, I have an additional terminal open to the server VM, where for one of the demos, I'll be showing some dmessage output. I have a script on each host that allows me to specify a Lustre version. The script configures ETH2 and ETH3 on the TCP1 network. And you can see that if I specify 2.12, the version being used is the latest 2.12.8 LTS release. And if I instead specify 2.15, again, we place the same configuration, but now the version being used is the RC3 candidate. Our first demo is on how the discovery feature affects the multi-rail feature. We'll start this demo by configuring LNet on the server and the client using Lustre 2.12. We can see that discovery is enabled by default on both the server and the client. Now we discover the client from the server. This creates a multi-rail peer entry on the server for the client. The server also pushes its configuration to the client, allowing the client to create a multi-rail peer entry for the server. Now, some changes to the LNet configuration will be pushed out to our LNet peers. If I delete an interface on the server, we can see that the client has automatically updated its peer information to reflect that configuration change. Now note that even though this server now only has a single LNet NID, it's still considered a multi-rail peer, which may be a little confusing because it only has one rail, so to speak. But this multi-rail field in the peer information is really about capability. So the way to read this is that this peer supports the multi-rail feature set, regardless of how many interfaces it actually has configured. So now I want to do the same thing, except I'm going to disable the discovery feature on the server, and we'll see how that changes things. So we disable discovery using the LNetctl set discovery command, and we can see that that change took effect. And now we'll discover the client from the server, and we can see that with discovery disabled, we've created a non-multi-rail peer entry for the client. With discovery disabled, any peer that the server creates through discovery will be non-multi-rail. And in this particular case, with Lustre 2.12, the client does not create any peer entry for the server as a result of the server's activity. So let's discover the server from the client, and we can see that a multi-rail peer is created for the server. So let's repeat this one more time, and this time we'll use Lustre 2.15 and see how that changes things. So again, I will disable discovery on the server and double check that it took. And now we discover the client, and again, the server creates a non-multi-rail peer entry for the client. And so nothing on the server side appears to have changed. Looking on the client side, we can see that the client has created a peer entry for the server, a non-multi-rail peer entry. Let's go ahead and delete that. Oops. So we've deleted that peer entry, and now let's discover the server from the client, and again we can see that it resulted in a non-multi-rail peer entry for that server. So there are some subtle differences here in that in 2.15 the client creates a non-multi-rail peer entry for the server. Now even with discovery disabled on the server, we can still create multi-rail peer entries using the command line interface. So the takeaway here is that the multi-rail feature is controlled on a peer-by-peer basis. And in Lustre 2.12, if discovery is enabled locally, then multi-rail peers are created by default by discovery. In Lustre 2.15, discovery must be enabled on both peers in order for a multi-rail peer entry to be created by discovery. If discovery is disabled on either peer, then a non-multi-rail peer entry will be created, regardless of whether or not discovery is enabled locally. And even with discovery disabled, we can always create multi-rail peer entries using the CLI. The next demo is on how to view the state of LNet health and related activities. We start with the same setup as the last demo, with Lustre 2.12 and LNet configured on ETH2 and ETH3 on TCP1. I will discover the client from the server, and now I want to simulate some failures, so I'm going to add what are called drop rules. And what this drop rule says is that any traffic sent to the client's ETH2 interface is going to be dropped, and we're going to simulate a network timeout for LNet health. And I'll talk more about what that means in a bit. Now I'm going to add an additional drop rule that does pretty much the same thing, except for any traffic sent to the server's ETH2 interface is going to be dropped, and a local timeout will be simulated for LNet health. Now I'm going to issue some pings, one to the client and one to the server's ETH2 NID. And we can see that both of these pings failed because they hit these drop rules. So this is just a tool that is used by development for debugging and testing. So the first thing that I want to look at is how to actually inspect the health values that are part of the LNet health feature. So we can inspect the health value of the client's interfaces with the LNetctl peer show command. You can specify the NID of a LNet peer that you're interested in, and you need to specify a verbosity of at least 2. Now this command outputs quite a lot of information, so we'll just prune it with this grep command so that we can focus on the information we're interested in. So here we see the NID for each of the client's interfaces and the associated health value that LNet is keeping track of. So we can see that the ping failure and the simulated network timeout caused the health value of the client's ETH2 interface to be decremented. 1000 is the maximum value that LNet will set. Now we can inspect the health value of local interfaces using the LNetctl net show command. Again, a verbosity of at least 2. And here we see the health value for the server's ETH2 interface is at the maximum. And for the ETH3 interface, the health value has been decremented. Now, LNet relies on lower-level network drivers to tell us whether a failure was due to a problem with a local interface or with the remote destination interface. This is referred to as the LNet message status. If we take a look at the code, we can see that there are a variety of message statuses that can be set by the network drivers. When one of the local message statuses is set, that tells LNet that there was a problem with the local sending interface, and LNet can choose to decrement the health value of that interface as a result of that status. And when a remote status is specified, you guessed it, that's telling LNet that there was a problem with the remote destination interface, and LNet can choose to decrement the health value of the destination. Now there's another status, which is the network timeout, and that basically tells LNet that the driver doesn't know if the problem was a local one or a problem with the remote destination one. And in this case, what LNet should do is decrement the health value of both the local interface used for the send, as well as the interface for the destination. This doesn't work correctly in Lustre 2.12. The ticket for that is LU13571, but that is fixed in Lustre 2.15. Now, when the health value of an interface is decremented, that interface is placed into a recovery mode where it is periodically pinged to determine when it can be returned to service. We can print the list of interfaces that are in recovery using the LNetctl debug recovery command. The -p flag will print the remote peer-and-I recovery list, and a -l flag will print the local interface recovery list. Here we see another bug in Lustre 2.12, where we have a local interface that is in the peer-and-I recovery list. The tick for that is LU15398, and that issue is also resolved in Lustre 2.15. In Lustre 2.12, interfaces in recovery are pinged at a fixed interval, and by default, that interval is 1 second. Now let's remove that drop rule for the local interface, and that should allow the health value to start recovering. We can see that it'll be recovering from 0. While we wait for that interface to recover, we can look at some additional information about LNet health. LNet keeps a tally of how many times these different health statuses were reported by the network drivers. These stats are also available with the peer and net show commands. So here, taking a look at the peer network interface stats, we can see that the network timeout message status was reported 8 times. And with the net show command, we can see the local message statuses, and we can see that the local timeout was reported 27 times. Now, these are just running tallies, so if you want to see what types of errors are being experienced in the moment, you can dump these over time and just see how these counts are increasing. Another option is that we can modify Lustre's debug mask and inspect some messages that are printed to Lustre's debug buffer. This command enables the printing of messages in the LNet layer to Lustre's internal buffer, and this command will dump that internal buffer to a file, and then we can inspect that file for these LNet health check strings. And if we just look at the last 3 entries, we can see that the last 3 transactions all completed okay. And that's not terribly interesting, so let's prune out all of the messages that are reporting okay. And if we look at the last 3 errors, we can see the local timeout and the network timeout is being hit. And of course, in this case, that's because of the drop rules that we added earlier. So what this says is that, and I apologize for the line wrap making it a little difficult to read, but so here you can see that we sent a message from the servers 12 at TCP1 to the servers 11 at TCP1, and that hit the local timeout. And then for this next one, we sent a message from the servers 11 at TCP1 NID to the clients 15 at TCP1 NID, and that hit the network timeout. Okay, let's check on how our local interface is recovering. And if you recall, we were starting from a health value of 0, so it's now up to 504. And in Lustre 2.12, that health value is going to increment by 1 on every successful send to this interface. And in Lustre 2.15, the only difference there is that it will increment by the same amount that it decrements, which is configurable with this health sensitivity parameter, which defaults to 100. Now let's turn our attention back to the recovery of the client's interface. We still have the drop rule in place for the client, so its health value is not able to recover. In order for an interface to be taken out of recovery mode, its health value must reach the max of 1000. This means that if a client that is in recovery is taken out of service, its peer interface can become stuck in recovery. This results in the server continually pinging a dead client. Furthermore, if this client is brought back, it may come back with a different LNet configuration, which could be the case if it had new IP assignments, for example. So this would result in the server continually pinging a dead client, which can fill up the logs with error messages and just otherwise be some unnecessary work. There is an easy remedy for this, which is to simply delete the stale peer entry on the servers using the LNetctl peer delete command. And we can see with the peer deleted that its interfaces are no longer in recovery. Now there are some changes to how this works in 2.15, so we'll take a look at that next. Okay, I've set things up in a similar manner as before, but now we're using Lustre 2.15, and rather than discover the client, I've added a peer entry for the client manually using the command line interface. The reason I added the peer entry manually is that I want to show what happens when we haven't received a message from the client's ETH2 interface. So here we can see that the receive count for that interface is 0. Now if I issue the ping and we trigger the failure, we can see that the health value has been decremented as we expect. However, if we look in the recovery queues, we see that none of the client's interfaces have been put into recovery mode. The reason for that is in Lustre 2.15, LNet will not put an interface into recovery mode unless we've actually received a message from it at some point in the past. So consider a situation where LNet is asked to send a message to a peer that it is unable to communicate with. In Lustre 2.12, in this example, I'm pinging some NID that I made up. And in Lustre 2.12, this would result in a peer interface being created for this NID and immediately put into recovery queue. And it would be stuck there forever until we deleted that interface as we talked about with 2.12. So Lustre 2.15 avoids this situation by requiring that we receive a message from an interface in order for it to be eligible for recovery. So I'll delete the drop rule on the server and issue some pings on the client to the server and do a couple here, and we'll double check that we actually received a message. So we received a message from both of the client's interfaces. So now they should both be eligible for recovery. Add our drop rule back and issue the ping. And now we'll see the health value has been decremented as we expect, and we should see the interface in the recovery queue again as we expect. So the other difference with Lustre 2.15 is that interfaces in recovery are no longer pinged at a fixed interval. Instead, we keep track of the number of recovery pings that we've sent to an interface in recovery, and we use that to calculate in kind of an exponential backoff for when the next ping gets scheduled. So the very first ping, the very first few pings are sent pretty quickly after a few seconds, and then as this ping count increases, we'll extend that ping interval all the way up to 15 minutes. So this is to handle situations where an interface on some peer has failed and it's out of service for an extended period of time. We don't want to be aggressively pinging it once every second or whatever. We want to be a little smarter and just ping it on occasion. When we receive a message from an interface that's in recovery, that resets that ping count. So if the failed interface is returned to service on the client will start using it. And when the server receives a message from that interface, it will reset that ping count so that we recover it more quickly. So here we can see that ping count has been reset after we sent a couple pings from the client to the server. The last difference with 2.15 that I'll highlight is that there's a new option to allow peer interfaces to age out of recovery. This is controlled with the recovery limit parameter. And by default, we do not age out interfaces. But if you wanted LNet to stop trying to recover an interface after, say, 1 hour, you could set this parameter. The value is in seconds. And this just means, like I said, after this amount of time, LNet will remove an interface from recovery mode. Local interfaces cannot be aged out of recovery because LNet relies on those recovery pings to tell us when we can start using our local interfaces. But a peer interface that has aged out can become eligible for recovery again after we receive a message from it. The next demo demonstrates how the primary NID is referenced by Lustre. For this demo, I've created a file system on the Lustre server and mounted that on the client using Lustre 2.15. The LNet configuration on the server is the same, 2 NIDs on TCP1. The client configuration has been modified, so the client now has 2 NIDs on TCP99, including its primary NID, in addition to 2 NIDs on TCP1 that are used for Lustre. The server dmessage output is being printed on the bottom. I want to trigger network errors on the server, so I add a drop rule, and we can see that error messages from LNet will reference the client's TCP1 NIDs that are actually being used for Lustre traffic. But error messages from Lustre itself, such as this one from the MGS, will reference the client's primary NID. Again, the primary NID is just a unique identifier for a multi-rail peer. So all this message is saying is that the multi-rail peer with this primary NID is reconnecting. It does not mean that this client is reconnecting using that TCP99 NID. That is impossible because the server does not have any NIDs on the TCP99 network. Now I want to show what happens when the LNet configuration on the client is modified such that it gets a new primary NID. I've deleted the drop rule on the server, and now I'll delete the LNet configuration for the primary NID, and we can see that it has a new primary NID, 16 at TCP99, and in Lustre 2.15, that change is propagated out to the servers, so we can see the updated peer information for the client here. Now if I add that drop rule back on the server, we again see that LNet errors will reference the client's TCP1 NIDs that are used for Lustre. But error messages from Lustre itself can still reference that old primary NID. This makes it challenging to diagnose issues based on these Lustre messages. Because if you see this message in the server logs and you want to go investigate this client that's having an issue with connections, this NID is no longer referenced anywhere in the cluster, neither on the server side, nor is it in the client configuration. So that just makes troubleshooting these issues difficult. My recommendation would be to avoid modifying the LNet configuration while Lustre is mounted. Instead, simply unmount Lustre from your clients, unload the LNet modules, and before you make any changes, if you really want to be thorough, I'd recommend deleting these old peer entries from the servers. Then you can load LNet with your new configuration. So here I've gotten rid of the TCP99 NIDs, and we can mount Lustre on the client. The server sees this as a brand new Lustre client, so it's no longer going to associate those old primary NIDs with this client, which we can see if we add this drop rule back. Again, all the messages from Lustre will be referencing the client's new primary NID, which is 15 at TCP1, which we can see here. For the final demo, we show how the LNetctl Ping command can and cannot be used to find broken paths. I've configured LNet with Lustre 2.12 on the server and the client with the same configuration we've been using, ETH2 and ETH3 on the TCP1 network. And I discovered the client from the server, and after discovery, I've added this drop rule on the server so that every message that is sent to the client's ETH2 interface, 15 at TCP1, will be dropped, and a network timeout will be simulated for LNet health. Now, let's say I want to make sure that these two peers can talk to each other. So I execute some ping commands to make sure that LNet traffic can flow between the two peers. And so right away, I try 15 at TCP1, and that fails because of this drop rule. And so now I'll try 16 at TCP1, and that works fine as we'd expect. So right now, it looks like the ping command has correctly identified that there's some problem with the 15 at TCP1 interface, and the 16 at TCP1 interface is working fine. But now if I repeat this, so suddenly the 15 at TCP1 interface seems to be working fine. And in fact, I can keep sending these pings and they work. So that's weird because we know that we specifically told LNet to drop every message that's being sent to 15 at TCP1. So what's happening here is that when we hit that very first failure, we simulated a network timeout to LNet health, and so that decremented the health value of that 15 at TCP1 interface. So all of these subsequent pings, even though we specified 15 at TCP1 as the destination, they've actually been routed to the 16 at TCP1 interface. So this ping argument isn't, it's not specifying a specific endpoint where the ping will be sent. It's really specifying a peer. And LNet is free to select any available interface for a multi-rail peer. And so this makes it very tricky to diagnose connectivity issues in Lustre 2.12 using the LNetctl Ping command, because you really need to account for the health values and where LNet is actually routing traffic. Okay, so now I'm going to repeat this exercise with Lustre 2.15. The setup is all the same. So now I'm going to issue the first ping to the peer, and that seems to work fine. Do it again. Now we hit the failure, and as before, after we hit that failure, health has been decremented, and so all the future sends are being routed to 16 at TCP1. But in Lustre 2.15, we have an additional option for the ping command, which allows you to specify a local NID, or the source interface for that the ping will be sent out from. And when you do that, that fixes the specified destination. So when the source interface is specified, the destination endpoint is not changed. LNet will honor the destination specified, and so that allows us to actually send a ping to that 15 at TCP1 interface, and we can specify both of our local interfaces and say, okay, so we can't send to that NID from either of our local interfaces. But then we can check the client's other interface and we say, okay, so it looks like the problem is specific to that, that ETH2 interface. So that provides us an additional way to help narrow in on network issues. This concludes the demo. I'd like to thank you for attending, and I encourage you to reach out to me with any questions, comments, or feedback.
Thank you, Chris, for this video about LNet. I think it's going to be the new reference video for troubleshooting LNet. I don't know if you are able to join us live, but I encourage people to post questions for Chris in the Q&A. I have a question myself. If Chris, you are here, that you are troubleshooting LNet between 212 and 212 servers and 212 clients, or 215 servers, 215 clients. We expect in the future to have a mixed version of Lustre, or 212 with 215, which is the next LTS. So do you have any tips or recommendation on using LNet in a mixed environment?
Yeah, I mean, I think we will learn more about that as 2.15 adoption of 2.15 becomes widespread after its release. But I think that the general thing to keep in mind is that when you're trying to troubleshoot multi-rail issues, LNet is making decisions on how it behaves based on the version of the local node, right? So if you're looking at a client and that client is 2.12, LNet, that client is making decisions based on the feature set in 2.12. And that's kind of what I was trying to highlight with the example with how the discovery feature, there's subtle differences between 2.12 and 2.15. So a 2.12 client discovering or a 2.12 peer discovering a 2.15 peer, is going to be different than vice versa. So you just have to kind of keep that in mind, that there can be subtle differences with how these versions behave locally, and that can have implications, for the cluster wide. But again, I think we'll learn more about any potential nuances like that between 2.15 and 2.12 as 2.15 gets wider adoption.